Assalamualaikum student. Okay, so this is a recorded session. Okay, uh, for the topics on the curl divergence and also Stokes theorem. Okay. So in our previous class, yeah, you have seen about the Green's theorem. Okay, so this time I'm going to explain on the Stokes theorem. So in the Stokes theorem, there is a concept on the curl or and also divergence. Okay, so we start with the curl, as you can see on this ebook. Okay, so we'll start with the curl. Okay, so let's say we have the vector f given p I plus qj plus rk. So the curl is given here. Okay, the concept is we are supposed to find the partial derivative for r with respect to y, subtract with partial derivative of q with respect to z. Okay, so it's given with that with this kind of symbol, but it has the same meaning by evaluating the partial derivative. So which part is the x, y, z? Is this one. Okay, so from p for q from r. Okay, so you have seen about the gradient. Okay, so we have the gradient operator that is defined by partial derivative of x at vector I plus partial derivative of with respect to y at j vector and partial derivative for with respect to z at the k vector. Okay, so if we multiply this, so we have gradient f, so everything on the right hand side will be multiplied with f, okay, or it will be combined with um, functions f. Okay, so in this gradient vector, okay, so this is the gradient symbol. When we have the multiplication with the vector field f, okay, so we reach at the curl f. Okay, so the curl f, so this is given in the words. It is equivalent to this kind of symbol. So this is also called as the curl. Okay, so curl for vector f is equivalent to the gradient, okay, cross f. Okay, so this one we call cross product. Okay, so on our previous class, you will see about dot product, right? Okay, so there is another operations on the vector. So this is another one. Okay, we call this as the cross product. Okay, so the meaning for this curl f is finding the cross product between the gradient and the vector field. Okay, so the gradient here we find it as the vector ijk. So we write down here. So the gradient will be our partial derivative, okay, at this level, and then the vector f is the one given in the vector field as pqr. Okay, so this is given generally. So if we know what is the vector field, okay, so we just replace the pqr here. Okay, so for this curl f, we will say example 1 here. Okay, so determine if the vector field given here, okay, is a conservative vector field or not. So conservative vector means if we get the curl f equal to 0, so the vector f is conservative vector. Okay, so if f the curl f is not equal to 0, so this vector f is not a conservative vector field. Okay, so for this, I'm going to explain how we do the determinant process for the curl f. Okay, so this is standard. We have I, j, k, then the partial derivative. Okay, so This is our P, this is our Q, this is our R. So don't forget about the negative sign. Okay, so we write down here P, Q, R. Okay, so to evaluate this manually, so I'm going to write down here for I. Okay, so at this column actually you can use pencil. Okay, so we just copy the same thing according to the column, first column. Okay, and then we have next column J. Okay, next we have okay, just write down the first two columns for I and J like this. Okay, so we are supposed to times out. Okay, which part that we're going to times out, follow this kind of direction. Okay, so I have here. Okay, so uh, okay, so this for this vector I, we are interested on this one, the partial derivative for this part. Okay, so when we multiply here, so it means that we have this function. So find the partial derivative with respect to y. Okay, so we have here as negative 2x squared y. Okay, so this is partial derivative. Okay, so there is a vector I actually. Okay, so that is here. This is vector I. Okay, then we continue for this one. So here is partial derivative for z for this one. There's no z here. Okay, so this is actually 0. Okay, so the one containing for the j vector, vector j now is 0. Okay, okay, for k here, find partial derivative for this one with respect to x. Okay, so we have yz. This is for vector k. Okay, and now we do it on another way. Okay, for the another direction that is here. Follow here. Okay, we start with I. Okay, so the one that for vector I, which is here. So this part, okay, find the partial derivative respect to z. So we have x, y. Okay, x, y. So this is for vector I. For vector j, so this is find the partial derivative respect to x for this one. So we have negative 2x y squared j. And for k is here. Okay, so this find the partial derivative respect to y. So we have x squared for the vector k. So this ijk is the vector. Okay, so ijk is a vector. Okay, so to combine them, we are supposed to deduct between here and here. Okay, and then we have this one 0 combined with here minus also. Okay, so this one combined with this one, so we just deduct. Okay, so this is 0 combined with here, just deduct. So there's negative and negative, so there will be plus. Okay, and we have k here, so this is yz, so we have to deduct with x squared. Okay. Okay, so between them is the addition. Okay, so when we combine, we have like this. Okay, so we have to simplify for any part. Uh, So we check that the one that we evaluate for the curl is not equal to 0. Okay, we didn't get 0. So means that the vector field F is not a conservative vector. Okay, so that is for the curl. So we are going to see for the divergent F. Okay, so the divergent F is the dot product between the gradient and the vector field. Okay, so the dot product means we are looking at the scalar and the gradient. So we just multiply the scalar gradient with the scalar at the vector F. Okay, so this is for the example. Uh, we have this divergence F. So this is the vector field F given here. Okay, so our gradient here is this one, partial derivative uh, with respect to x, with respect to y, with respect to z. So they will just times up with the vector f, okay, as follow. Okay, so we have to evaluate the partial derivative here with respect to x. So we get 2x, 2xy, okay. Here, the partial derivative with respect to y, we have xz. And this partial derivative with respect to z, we have 0. Okay, so we have only at the first two parts containing of the partial derivative for x and y. Okay, so the third part is 0. Okay, so you have learned about this curl and divergence. So we are going to see the Stokes theorem. Okay, so this Stokes theorem is another important theorems like Green's theorem. Okay, so the Stokes and Green's theorems are mostly useful in engineering field. Okay, so I'm going to read regarding the Stokes theorem as follow. Let S be an oriented smooth surface that is bounded by simple closed smooth boundary curve C with a positive orientation. Okay, so means that we have from quadrant number 1 to quadrant number 4, and we have the vector field. Then Stokes theorem state that when we want to evaluate this kind of integral f dot dr, it is equivalent to double integral for the curl dot ds. Okay, so we will see example for this Stokes theorem as follow in example 1. So in problem, so in this example 1, use Stokes theorem to evaluate given here with this kind of vector field whereby S is the part of this one. You can see that this is in terms of three axes, x, y, z, and the plane z equal to 1. So if we want to evaluate this double integral, okay, the one given is on the right. So means that we have to work from the left one. Okay, so first we have this equation z, and we have z equal to 1. So we let these two equation equal. Okay, then we have the circle equation. So this is z equal to 1. This is another equation z. So we have this equation where we get this x squared plus y squared equal to 4 by simplify this above equation. So we can see this is equation of a circle whereby the radius is 2. Okay, so next we have to find the parametric equation for this problem. So because of this problem is the surface is based on the circle, so we are going to refer to the parametric equation for a circle. Okay, so a circle which is here. This is the guideline, remember? Okay, so because it is stated that positive direction, so we are going to use counterclockwise. Okay, so this is the x, y, so we just substitute what is the value of r. T limit is from 0 to 2 pi. Okay, so we combine the parametric equation as follow. Okay, so x equal to r is 2. Okay, r cos t. Okay, so this is y. Then z is equal to 1. Okay, so this is the parametric equation for this problem with the limit of t from 0 to 2 pi. Okay, so once we determine this parametric, then we plug it into the formula of f dot dr. Okay, so f dot dr means is the dot product between the vector f and our parametric equation. Okay, so f dot dr is equivalent with we plug in this rt into our frt. Okay, so this is x, y, z. So we plug it into the vector f given here. So everything that z squared 3xy x cube, y cube will be in terms of parametric. Okay. And then we differentiate this RT. So we have R prime T. Okay, so we just implement direct derivative for this part. Okay, so sin T we have cos T. So this differentiate 1, we got 0. Okay, so here we have negative 2 sin T. Okay, so we implement that into our methods here. Okay, and then we do direct integration. Okay, so this is the answer for FRT, and then this is the first derivative for R for the parametric, and then we do dot product. Okay, so remember the dot product is the multiplication between the scalar at the vector FRT and the first derivative. Okay, so where is the scalar? Okay, so at the vector I we have 1, and this one we have negative 2 sin T. So scalar, so we get here, this one. Okay, at the vector J, we have negative 12 cos T sin T. So we times with these 2 cos T. Okay, so we have this part. So the vector, at the vector K, we have 0 actually. Okay, so this that's why in the dot product, it is 0. Okay, so this is our final value for the dot product. Okay, so and then we plug it into the formula just now. Okay, so then we have the limit from t0 to 2 pi. Okay, so this, for this part we do direct integration. Okay, so here we are using trigonometry identities. Okay, so this one you can refer to the trigo identities, the formula. Okay, so then we have the final answer for the curl that is equal to 0. Okay, so if there's anything that you want to ask me, you can ask me. Okay.